Section 2.4, the close packing of spheres. So first, let's look at a simpler two-dimensional close packing scenario. Those are two-dimensional atoms. They are close packed, and we can calculate the packing efficiency by drawing this rhombus with a silence of 2r. So this is r, this is not r. This is r, this is not r. The area of this rhombus is very simple. It's just this silence multiplied by the height. The height is the square root of 3 times r, because this angle is 60 degrees. So the area is 2r times the square root of 3r. What about the area occupied by the atoms? It's very simple. If you piece these two together, it's 1/2 of the circle. Alright, you can put this part to here. And then same, the sum of this area and this area is 1/2 of the atom. Alright, so together, you have just one atom in the rhombus. Therefore, the area occupied the 2D atoms in this rhombus is simply pi r squared. And then you just need to do a division. You have pi r squared on top. You have 2 times square root of 3r squared on the bottom. You have 90% efficiency over here. But this is just a simpler two-dimensional analog of three-dimensional close packing. This is three-dimensional close packing. Well, now you have to imagine those are spheres. Those are not circles. You have 5 by 4, 20 spheres over here. And then you can put another layer of spheres on top of the first layer. So I'm going to call the second layer B layer. You can put atoms in the B layer, the second layer, and then the third layer is going to be either A layer again or a new C layer. Alright, so it can be A layer again or C layer. So what's the difference? Well, let's look at this picture. So first, this A layer, light blue. And then B layer, orange. And then the third layer, A layer again. Look, this purple A atom over here in the third layer sits on top of an atom in the first A layer. So exactly on top. So that's why we call this A layer again. And then on top of this A layer, you're going to have another B layer. So it's going to be A, B, A, B, A, B. Over here, A layer, B layer. Okay, now C layer with a different green color. Look, this C layer does not sit on top of any atom in the B layer or A layer. So these 3 layers are different. Now you have A, B, C, A, B, C, A, B, C pattern to form this crystalline structure. So again, these two, although they are both close packing structures, but you have AB, AB, AB here, and you have ABC, ABC, ABC here. Now let's look at the same structures from a different perspective. So again, you have ABC layers, and you can see in the C layer, you have green atoms. They do not sit on top of any B atoms or A atoms. This is ABA, 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 and you can see in the third layer, okay, you have atoms sitting right on top of the atoms in the first layer, so we call this AB, AB, ABA. There are other names for this kind of close packing structures. So this is so-called cubic close packed structure, or CCP. This is called hexagonal close packed structure, or HCP. Okay, so CCP versus HCP. This is because this one is called HCP. Again, you can see those hexagonal structures easily. But why is this one called a CCP, cubic close packed structure, or even face-centered cubic? Okay, FCC, face-centered cubic, is cubic close packed structure. These two different names are referring to the same structure. Why is that? It's very hard to see a cubic from this picture, but if you look at a cubic, a face-centered cubic structure, All right, from this corner to that corner, it's gonna look like ABC close packed structure. So let's look at this structure here. You know it's a cube, and we have 8 atoms on the corners, and we have 6 atoms on the 6 faces. All right, but then I'm gonna color these atoms in a different way. Okay, so these 2 atoms on the opposite corners, I'm gonna color them green. All right, and then this 6 atoms, okay, we're going to color them orange. So 1, 2, 3, 4, 5, 6. So these 6 are going to be orange. All right, and then finally the 3 on the bottom, this 2 here, on the centers of faces, and this on the corner, this 6 are colored blue. All right, now you have 3 different colors. You have blue here, you have orange, you have green, and then you rotate this structure. So make this one on top, this one on the bottom, and this 2 orange layer and blue layer parallel to each other. Okay, now you are looking at A, B, C layers. Okay, this is your layer A, this is layer B, this is layer C. So layer A, layer B, layer C. All right. So again, you can immediately tell layer C atom does not sit on any atoms in layer B or layer A. All right, so you repeat layer A, layer B, and layer C. You get the crystalline structure. It's called CCP or FCC. CCP, again, CCP here, it's cubic close packed CCP, or FCC, face-centered cubic. They are referring to the same structure. It's just you need to look at the same structure from a different angle. This is a cube, but if you look at this cube in this direction, from this atom to this atom, you're going to see 3 layers. Layer C, layer B, layer A, layer C again. All right? So again, this is the face-centered cubic structure over here.